All right, everyone. We are starting chapter 12 here, which is titled Statistics. And many of you have probably studied some statistics in some earlier classes and so on. Probably some of those concepts that you've talked about before we will be covering in section 2. But we need to start with some vocabulary and build with a foundation here that we're going to look at in section 1. And it is titled Sampling, Frequency Distributions, and Graphs. So let's get started on that. This is an example out of the first page in the chapter in your book. And actually there's a typo at the beginning in the book. It says here, I don't know if any of you remember the TV show MASH, but it was extremely popular when I was younger. And so that's what this example is talking about. At the end of the 20th century, there were 84 million households, and that's where the typo is. The original says 94 million, but it was 84 million households in the United States with television sets. The television program viewed by the greatest percentage of each household, or percentage of such households in that century, was the final episode of MASH. So 20th century, 1900, so toward the end of that in the 1990s, I believe is when that last episode was on. So over 50 million American households watched this program. Now the question is, how do they know that? How do they know that 50 million American households watched a date? That's our example here that we'll get to. So numerical information. Let's get some basic vocabulary done here. Such as the information about the top 3 TV shows of the 20th century, shown in the table 12.1 at the bottom of the slide here, is called data. And so we all deal with data of all kinds in our worlds, especially more and more. Certainly reading information on the internet, newspapers, any of that kind of stuff. The word statistics is often used when referring to data. However, statistics has a second meaning. Statistics is also a method for collecting, organizing, analyzing, and interpreting data, as well as drawing conclusions based on that data. This methodology divides statistics into 2 main areas. Descriptive statistics is concerned with collecting, organizing, summarizing, and presenting data. Inferential statistics has to do with making generalizations about and drawing conclusions from the data collected. So inferential statistics is kind of what do these statistics mean, and the descriptive statistics is just the numbers themselves. Okay, so this chart down here shows that the most widely watched TV show of the 20th century was that last episode of MASH, with over 50 million households watching it. Dallas was another popular show back then. The season ender was a major cliffhanger. If you ever heard the term "Who Shot JR?" That's where they left it. 41 million, almost 41.5 million people watched that last episode of that season. And then Roots Part 8. They actually kind of redid Roots here just recently. Had 36, about 0.4 million people watch it. So those were the top 3 programs, TV programs, watched in the 20th century. So consider the set of all American TV households. Such a set is called the population. That's another vocabulary term we need to know. In general, a population is the set containing all the people or objects whose properties are to be described and analyzed by the data collector. So the population is the big set of numbers that we're talking about in a particular example. Okay, that's called the population set. So the population of American TV households is huge. At the time of the MASH conclusion, there were nearly 84 million such households. Now, the question I kind of put, did over 50 million American TV households actually watch that final episode? What'd they do? Call every house and say, so, again, how are you? What'd you watch last night? No, that they couldn't have called 50 million households and asked that question and had that conversation. It'd take forever. So a sample of that population. So we have the whole population and then we have a sample of the population. A sample is a subset or subgroup of the population. Okay. In this case, it'd be appropriate to find a sample of a few thousand TV households, not 50 million. Okay, we would call or contact or get information somehow from a few thousand TV households to draw conclusions about the population of all TV households. So that's our sample. All right. So, for example, let's look at an example of populations and samples. A group of hotel owners in a large city decide to conduct a survey among citizens of the city to discover their opinions about casino gambling. So here's the question. A, describe the population. So let's do that first. Describe the population. Well, who do they want to survey? Who are the people that they want the information from? Well, it says they want to conduct a survey among citizens of the city, right? So the answer to A is the population is the citizens, all the citizens of the city. Part B, one of the hotel owners suggests obtaining a sample by surveying all the people at 6 of the largest nightclubs in the city on a Saturday night. Each person will be asked to express his or her opinion on casino gambling in the city then. Does this seem like a good idea? Or in other words, does that sample that he or she is suggesting, does it seem that that sample would represent the population being all the citizens of the city? Well, hopefully you would say no, right? Because if those people are attending a nightclub on a Saturday night, then the largest ones even, then they would probably be a little bit more open to casino gambling in their city than the average person who stays home on a Saturday night or even goes to a movie on a Saturday or whatever, right? And so that's a terrible idea. That would sway the votes and so on in this survey completely within that sampling. And so no, that is not a good sample. Okay. Let's look at another example here. A city government wants to conduct a survey among the city's homeless to discover their opinions about required residence in city shelters from midnight to 6 a.m. Okay, same questions. Basically, describe the population. So what's the population? Again, who do they want to survey? It says they want to conduct a survey among the city's homeless. So the answer to A, the population is a set containing all of the homeless people in the city. They would like to, if they could, survey all the city's homeless. Again, that's not possible probably. And so we want to talk about a sample. So part B, a city commissioner suggests obtaining a sample by surveying all the homeless people at the city's largest shelter on a Saturday night. Does this seem like a good idea? Well, maybe at first, that doesn't sound, I mean, it's a subgroup of the city's homeless population, right? And so really you kind of have to look at this as kind of answering the question of what's wrong with that group. Well, what would be wrong with that group is that they are people that are willing to come to a shelter. There are lots of homeless people that don't want to be in shelters because they don't want to follow any rules. And most shelters do at least have some rules. And so they don't want to be there because that's why that may not be why, but that for some homeless people, that is why they choose to be homeless, because they don't want to follow anybody's rules. And so this may not be a good sampling of the population here. So the answer here, no. People that are already in the shelters are probably more likely to be against mandatory residence in the shelters. Now that's even a little different take than what I was saying, is that their concept here is that if they're already in a shelter, they like it because they can come and go as they please. They can choose to be there or not. And so they would not want it to be required that they have to be in a shelter from midnight till 6. They're just choosing to do that, and they like to be able to choose to do that. And so that's why the book here is saying that maybe they would not be a good sample because they wouldn't want it to be required. So sometimes a sample can be pretty tricky. So you need to really think about that. So random samples. A random sample is a sample, from what we just talked about, obtained in such a way that every element in the population has an equal chance of being selected for that sample. So if we go to the 6 largest nightclubs, that's not a random sample. If we go to just the people that happen to choose to go to a shelter on a Saturday night, that's not a random sample. The population, it has to be every element in the population has an equal chance of being selected at random. Okay, so another example here, selecting an appropriate sampling technique. So we return to the hotel owners in the large city who are interested in the how the city's citizens feel about casino gambling. Which of the following would be the most appropriate way to select a random sample? A. Randomly survey people who live in the oceanfront condominiums in the city. B. Survey the first 200 people whose names appear in the city's telephone directory. Or C. Randomly select neighborhoods of the city and then randomly survey people within the selected neighborhoods. So think through each of those choices. Hopefully A kind of stands out, that again, people that just live in the oceanfront condominium, how does that represent all the population? That's a very specific and probably kind of an elite part of the population, right? If they can afford oceanfront condominiums, I don't know. Survey the first 200 people. That may sound kind of random, but it's not necessarily random, because there could be a slight inference there from those 200 people. The most random answer here is C. Randomly select neighborhoods of the city, so that's a random process in the first place, and then randomly survey people within those neighborhoods. That's a random sampling. Okay. Surveys and polls involve data from a sample of some population. Regardless of the sampling technique used, the sample should exhibit characteristics typical of those processed by the target population. Okay. This type of sample is called a representative sample. Okay. All right. Let's go on to frequency distributions. After data have been collected from a sample of the population, the next task facing the statistician is to present the data in a condensed and manageable form. In this way, the data can be more easily interpreted. And so typically when all those answers to the survey come in, we need to do something with them to where we're not just looking at a way long list of numbers. Okay? So we typically put them in a frequency distribution. So, for example, let's say the researchers are interested in determining the age at which adolescent males show the greatest rate of physical growth. A random sample of 35 10-year-old boys is measured for height and then measured each year until they reach 18. The age of maximum yearly growth for each subject is as follows. So 12, that means that one of these 35 boys, their maximum growth rate year was when they were 12. 14, the next set of data, that means that that boy of the 35, his maximum growth year was when he was 14. Another one was when he was 13. Another one when he was 14. And another one when he was at 16, and so on. And so there's 35 different, not necessarily different, but 35 ages there that represent those 35 10-year-old boys that were sampled over the next 8 years. Okay, with the largest, so like if we scan through there real quick, so only one of them grew the most in their 18th year of life, right? Yeah, and only one of them, year 10 was their largest growth rate. Everybody else was somewhere in between. All right. Well, instead of looking at that long list, which is kind of hard to go through and pick out, I was just kind of looking there to find that 10 and that 18. Instead of doing that, let's make a frequency distribution out of that. So a piece of data is called, each one of those is called a data item. This list of data has 35 data items. We've already kind of talked about that. Some of the data items are identical. 2 of the data items are 11 and 11. Thus, we can say the data value 11 occurs twice. Similarly, 5 of the data items are 12. So we say it occurs 12 times. So we're just going to summarize all those into a frequency distribution table. Okay? And so here it is. So the age of maximum growth, we already said that the beginning year of 10, there was only one boy that experienced their maximum growth in their 10th year. 11, 2 of them did. 12, 5 of them did. At age 13, 7 of them did. At age 14, 9 of them did, which is the greatest, right? Most of them said 14 was their biggest year. 15 was 6 people, 16, 3 people, only 1 at 17 and 1 at 18. That's a frequency distribution table. Just summarizing all of that data into one of each of the data points, which is 10, 11, 12, 13, 14, which is the ages, and then how many of each of the people in the population had that number as their data point. Okay, so that's a frequency distribution table. Okay, so I just kind of went through all that says. So most of them had their largest growth around age 14, because even the next largest was at age 13 with 7 boys, and then at age 15 had 6 boys. So the largest group was right around 13, 14, 15 years old. Okay. Much easier to see that in this way that the data is distributed here than when it's just in one long big list. Okay, let's talk about histograms and frequency. So here's our frequency table that we just had. Okay, we want to kind of transfer that to another kind of picture of what's going on to maybe help us see the data in a little different way. So we're going to convert this to what's called a histogram. Some of you might call this a bar chart, something along that line, but it's technically called a histogram. Okay, and so we are kind of plotting this on an XY plane in a way, and so we decide which of the planes, which one of the axes is which, and so we're going to put the data values at the bottom. Okay, that's typically the way a histogram is done. The data is at the bottom, and the frequency is the y-axis, the vertical axis. Okay, so at age 10 there was only 1. At age 11 there was only 2. At age 12 it jumped up to 5. At 13 it jumped up to 7. At 14 it jumped up to 9. At 15 it went back down to 6. 16 went back down to 3. And so from this histogram, again, we can kind of see that most of them were somewhere in the middle. And there were outliers at age 10 and age 17, 18. Okay, so it just gives us a kind of a picture of the data going on here. So that's a histogram. Okay. Let's look at the data a little different way. This is the last we're going to look at this. Stem and leaf plots, they're called. And so you may have been familiar with histograms. That's a fairly common tool. But stem and leaf plots, I'm not sure if you've seen this before, so be sure that you catch this. So let's look at a different set of data. This one might even be a little more confusing because it's kind of all over the place. But this is another set of the data, kind of like the 35 ages we had for the growth. This is test scores for a group of 40 students. Okay, and so they're just kind of listed. They're not in order. If they were in order, that would help us a lot. If they were listed from smallest to biggest, that would be helpful, or the other way around. Usually when I put test scores on a board, I go from largest to smallest and represent the stem and leaf plot that way. But there's a list of data. Might be helpful if we listed it in a different order, but that's the data that we're given. The plot is constructed by separating each data item into 2 parts. This is how a stem and leaf plot is created. The first part is called the stem. The stem in this set of data would be the tens digit. Okay, so for example, the stem of score 82 is the 8 because it's in the 80s range, and that's the stem. The second part is the leaf. Okay, the leaf consists of the units digit. So for that example, the 2 is the leaf of that data value. Okay, so the possible stems for this set of 40 scores up here are 4, 5, 6, 7, 8, and 9. There are no 30. There are no 30 scores in the set. There are no 20s. There are no 10s, and there are no single-digit ones, which would have a 0 for a stem. Okay, all the scores are between 40 and 90 something. Okay, so again, it would be best if we probably saw them listed in order. But here's the stem and leaf for this. Okay, so it starts again with 40. There are no 30s, 20s, 10s, whatever. So we start with the 4, and then we find all the 40s up there. Okay, well, the second number in the list is a 47, right? So there's one of them. There is a 45 and a 43 in the second to last row towards the end of it, 45 and 43. Those are all the 40s. So we put the stem out in front, the 40, and then we list it 7, 5, and 3 are there's a 47, there's a 45, and there's a 43 in the list. We do the same thing with the 50s. So there's a 57, there's a 54, there's a 56. Now typically in a stem and leaf, these would go, again, in order, either like the top row, 47, 45, 43 goes down. The second row here, that's kind of odd in a stem and leaf plot to just do them randomly. Typically they would either go up or down on all of the rows the same way. So this is a little bit of an odd example, but, and then the 60s, so 64, 63, 68, all those numbers are in here. So we can kind of see, in a way, it's almost like a histogram, sort of kind of sideways, to where there are more, we can see there are more 70s than any other score in this set. And the next most would be 80s, right? And so there are more grades towards the 70s, 80s, and 90s than there are below that. And so you can kind of get some pictures of those kinds of things going on in a stem and leaf plot. Okay? So in the homework for this section, you are going to be asked to create some of these types of things: frequency distribution tables, histograms, stem and leaf plots, and so on. And so you need to go and do assignment 12.1 now.